If we have a temperature change happen with a system in equilibrium, the equilibrium will shift, but it depends on whether the reaction is endothermic or exothermic. Let's first take a look at an exothermic system. So that is something that produces energy as a product. It gives off energy. So this is going to be some value in kilojoules. You can treat the energy term, or the kilojoules, like it's a product. And similar to concentration changes, if that temperature changes, it's going to be like changing the concentration for the product. So it will have the same type of reaction as if we were to change just C or D. If we were to increase the temperature in this system, we're increasing the amount of a product. So similar to the concentration changes, the equilibrium is going to shift to the left. It's going to want to get rid of this excess energy. It's going to react with C and D in the reverse reaction in order to try and restore equilibrium. An endothermic reaction is one in which the energy term is a reactant. If we were to increase the temperature with an endothermic reaction, it's effectively like we're increasing the concentration of a reactant. So similar to if we were to increase the concentration of A or B, if we increase the temperature here, the equilibrium is going to want to shift to the right. It's going to want to use up this extra energy. It's going to create more C and D. It's going to decrease the concentrations of A and B in order to try and restore equilibrium. Volume changes get a little bit trickier. What we have to do is consider the total moles of reactants versus the total moles of products if everything is in the gaseous state. So volume changes only really apply to those reactions with chemicals that are in the gaseous state. If we were to decrease the volume of the container here, we need to recall that V is proportional to 1 over P because PV equals nRT. So if A, B, C, and D are all gases, then let's see what happens to the volume. If we look at the total moles of reactants, we have 1 mole of A and 2 moles of B, so that makes 3 moles total of gas reactants. If we look at C and D, our products, we have 1 mole each, which means we have 2 moles of products. So 3 moles of reactants, 2 moles of products. If we decrease the volume of the container, what will happen is the equilibrium will shift to the right because it's going to want to go from 3 to the lower number of 2. And that's in order to decrease the pressure because the pressure is proportional to our volume. If we have less moles of gas in a smaller container, it's going to decrease the pressure of the system. So if we have equal moles of reactants in products, as in this example here, A plus B reacts to give C plus D, we have 2 moles of reactants and 2 moles of products. If we were to decrease the volume of this container, there would be no shift in equilibrium because the moles of the reactants is equal to the moles of the products. There really isn't a lower number here, so there's not one side that's going to be favored.